So what's part 2 about? Well, if I go back to part 1, I said the derivative of the integral is the original thing. So part 2 involves definite integrals. So when we look at part 2, what are we concerned with? We have this picture. We got sort of a set of axes. Here's A, here's B. You have some function like this. This is y is equal to f of x. And your goal is to calculate what this area is. And we write this as the integral from a to b f of x dx. Okay. Now here's what I want to do. I want to basically say, let capital F of x be the function such that f prime of x, capital F prime of x is equal to little f of x. Can anyone use a different term to explain what this says? What can you say capital F is? Capital F is the function, so when I take the derivative of it, I get lowercase f. So can anyone rephrase the sentence using a term? Antiderivative, that's right. So we're basically saying REF is the antiderivative of little f of x. Okay. So here's what the fundamental theorem of calculus part 2 tells us. It says, if you want to find the integral from a to b of lowercase f of x dx. Another way of saying that is, if you want to find the integral from a to b of the derivative of capital F of x dx like this, this is equal to just capital F of b minus capital F of a. This is what the fundamental theorem of calculus part 2 tells us. Okay. And I want to interpret this for you. So just take a look at this. It basically says, if you started with some function, then you took the derivative, and then you integrated, you basically can take your original function and just plug in the endpoints, and that will give you the area. Now, I don't have a lot of time to talk too much about how great this is, but this theorem is pretty amazing. Why is this theorem amazing? It's amazing because you could take your little picture over here, this is lowercase f over here. This theorem basically says your area only depends on the antiderivative and just 2 points in the interval. So just knowing the y values of the antiderivative gives you the entire area. That's kind of amazing. Like, how come you don't need to worry about any of these other points? How come you only need to plug in 2 endpoints, and that'll give you the whole area? Now, you don't plug it into the original function, you plug it into the antiderivative. That's amazing. So, I don't know, sometimes it's, well, I can't talk too much about it. Let's work on some example problems, but this is kind of amazing. So let me show you an example. This example is I probably did this on the video, but I don't remember. I tend to choose the same examples, unfortunately. So let's say I'll choose a different, more unusual number. I'll go from 0 to 6 of x squared dx. Okay. So what, before we did it the long way, 4.1 and 4.2, really 4.2, that's the long way. That's what your quiz is going to be on next week. That's kind of a pain in the neck. But the easy way just says, find the antiderivative. The antiderivative of x squared is x cubed over 3. And we just plug in the endpoints. So we use a vertical bar. We put the lower limit at the bottom and the upper limit at the top here. And then we just plug it in. So this will be 6 cubed over 3 minus 0 cubed over 3. That's just 6 cubed over 3. That's it. Easy peasy. Does that make sense? I want you to try a couple